Hi everyone, welcome back. So I'm really excited in this lecture to tell you about one of my favorite algorithms, kind of modern algorithms, called robust principal component analysis. So the regular principal component analysis is one of the absolute most important algorithms of the last 100 years. You see this everywhere. It's right up there with the fast Fourier transform is principal component analysis. This is a cornerstone, a mainstay of statistics and modeling big data. So if you're interested in machine learning, big data, you've definitely seen principal components analysis before, and you've probably used it. Okay, and so what we're going to talk about today is how can we use sparsity to improve the principal component analysis to make it more robust to outliers, to corruption, to bad data measurements. And this is based on a recent paper by Candes, Lee, Ma, and Wright from 2011, which really beautifully outlines this theory and shows how to use it. Okay, and what I'm going to talk about in this lecture, just as kind of a hook to get you interested and to kind of get through the math, is this basic problem here. What if we had a picture of a person? We knew it was a person, but it had this kind of big, funny mustache. Or maybe the person was wearing a hoodie or trying to disguise themselves and hide from some security camera. Can you, with modern robust statistics, with modern tools and kind of machine learning and optimization, can you figure out what was under that mask and kind of subtract off that mustache or that hood? So can you decompose an image into the true underlying system, the underlying measurement, and kind of the mustache and fake glasses and hood? Okay, and surprisingly and slightly alarmingly, the answer is, in many cases, yes, you absolutely can. So you can no longer kind of get the cartoon fake nose and mustache and glasses and hide from the cops, because based on pretty recent advances in sparsity and robust statistics, you can actually start to figure out what's under those disguises. Very cool. Again, a little bit alarming, but I'm going to walk you through all of this and how this works. Okay, and there's no magic happening. This only works because I know that I'm looking for pictures of a person. Okay, I couldn't. So I'll walk you through all of why this works and how this works and some of the math underlying this in this lecture. Okay. Again, this is following chapter 3 from our new book by myself and Nathan Kutz, Data-Driven Science and Engineering. If you want to read about this, download the PDF here. All of the code in MATLAB and in Python are on databookuw.com and on GitHub, so you can kind of walk through these examples yourself, okay, and use this. I think you should be using this in your daily life and in your research. This, anytime you would use principal components, you should be using robust principal components. Okay, so as a little motivation, we've seen before kind of this robust regression idea. So if I'm going to do a least squares regression, maybe I have these blue data points and I want to fit a line to those data points, but maybe I have a really bad outlier. I have one measurement that's way outside of the distribution. Maybe someone just messed up the instrument or kicked the thermometer or whatever you're measuring. Someone just messed up the measurement here, but everything else is okay. And so we've seen before that even though there is this true kind of slope, this true fit, regression fit for the bulk of the data, if you do something like a least squares regression, this L2 minimizing regression, then this is going to be strongly skewed by this outlier. And it's actually going to tilt the entire regression fit to get closer to that outlier, because the sum of the squares of the error, the square of this error, is so much larger than the squares of all these other little errors. Okay, and so what this tells you is that standard least squares regression is very, very fragile or sensitive to outliers. It tilts the whole regression fit, and we're going to see that that's exactly also true of principal components. But what we've also seen is that if you use an L1 regression, so instead of penalizing the sum of the squares of the errors, you penalize the sum of the absolute values of the errors, this L1 error norm, you get a much, much more robust and faithful estimate of the original distribution, even given this outlier. So it's much more robust, and it has this outlier rejection property. Okay, so that's exactly what we're going to be doing here with this robust principal component analysis. Again, you have some cloud of data with an outlier. There is some true distribution that you're assuming can be well modeled by a Gaussian, by some kind of a tilted, stretched out Gaussian, which is the normal principal components analysis assumption. But when you do standard PCA, just kind of vanilla off-the-shelf PCA, that whole distribution is going to get, again, tilted down to be closer to this outlier. It's going to tilt and stretch and distort the distribution because of that one outlier. So again, I can't stress this enough. Regular principal components analysis, it handles small amounts of like white noise, but outliers and corruption that are well outside of your distribution, that are kind of really bad measurements, will completely skew your PCA. And so PCA is also very fragile with respect to outliers and is very sensitive to them. And so what we're going to see is that this robust principal component analysis, just like our robust L1 regression, is going to kind of compensate for, knowing that there's outliers. It's going to use an L1 penalized regression, and it's going to fix this this principal component fit. And so you're going to get much closer to the true distribution, and you're going to have a lot more robustness to corrupt and outlier measurements. Okay, this is just the cartoon. I'm going to walk you through the math now. Okay, so if we go back to kind of this original paper, this RPCA work by Candez, Lee, Ma, and Wright, we're still talking about this basic idea. Let's say I have a high dimensional measurement. So I always think of pictures as really, really high dimensional measurements. Maybe a megapixel image is a million tall vector in my world. And so we have this high dimensional measurement, and we know that some of the pixels are corrupted. So this is not an example from their paper. They have a little bit more serious examples. This is a silly example from our book where I add this goofy mustache. And so you can see that something like 20% of the pixels are just completely wrong. I've completely obliterated them and turned them into just black pixels. So that's kind of what I mean by an outlier or by a corruption. It's not just my face with some white noise on it. It's just I've erased that information, and it's outside of the distribution of what a face looks like. Okay? And so the question is, how can we split this X data into some component that is true and correct, and a sparse matrix with all of these outliers? And you can see that there's a ghost, a faint picture of his face, but this is pretty small in magnitude. This matrix is mostly sparse and mostly, it's almost all zeros. All of this stuff is almost zero. And then this mustache is a sparse collection of all of the corrupt outlier measurements from the original data. So how do I split my data like this? Why can I split my data like this? That's what I'm going to talk about. And the basic idea is you couldn't do it if you didn't have a large library, a large kind of statistical knowledge of what a human face should look like. Okay, so you couldn't do this if you didn't know what a human face looked like. If you didn't have a training data set, so in kind of the machine learning speak, you need a large training data set to learn the statistical features of what's in a human face, and then you can do this robust principal components. Okay, and so the basic idea, this is from the Yale Faces B data set. So you have 36 individual people, and for each of those 36 people, you have 64 images of that face with different lighting conditions. It's actually a really cool experiment. They built this geodesic dome with all these cameras and lights, or rather all of these lights and then a camera. And in 2 seconds, they would flash all of these lights and take 64 images to get all of these different lighting conditions. Okay, so it's a really massive library of what human faces should look like under different lighting conditions. And the idea is that if you have that data set, even if one of your images has pretty bad corruption, maybe even if I like black out half or a quarter of these faces, or I put a big curly mustache on one of them, because of the statistics of this data set, you can essentially separate out the data set into what's called a low rank component that's well described by principal components, and a sparse component that has all of the outliers and all of the kind of weird, corrupt, bad measurements. Okay, and there's a lot more depth here, so I do encourage you to read their paper and read this in chapter 3 of our book if you want to know more, or check out our code. I'm just giving you kind of the highlights right now. Okay, so the basic idea is that you would take all of these faces, 64 times 36, you would reshape each of them into a really tall, skinny vector. So now you have this massive, massive matrix, number of pixels by number of images. And what we're going to do is we're going to do this robust principal component analysis to split kind of that big data matrix into a low rank matrix, a matrix that is well described with principal components with low variability. And this is what's called our eigenfaces. So if you take the SVD of your faces, you get these eigenfaces. That low rank matrix would have your eigenfaces. And then plus a sparse matrix, which has all of the stuff that's not in that distribution of what a face should look like this curly, weird mustache that I added. Okay? And so the math problem is really actually very simple to write down. We're trying to decompose X into the sum of two matrices, L plus S, where L is low rank, meaning it's well described by a few patterns, it's well described by principal components. And S is a sparse matrix with all of the corruption and outliers and bad measurements, okay? But you'll notice this is not a well-posed problem at all. There are infinitely many ways I can split a matrix X into a sum of two other matrices. This is kind of like I have n knowns and 2n unknowns. So it's completely ill-conditioned and underdetermined. And there's infinitely many solutions to this problem, but we're getting really good at that. That's becoming a common theme nowadays in optimization and statistics and sparsity and machine learning in general, is that you can solve these ill-posed inverse problems if you regularize, if you add a penalty term that promotes a single solution that has the kind of physics or behavior that you want. And in this case, what we actually want to do, the properties we actually want on L and S, is that we want our L matrix to be low rank, so it's well described by principal components. So we want to minimize the rank of L. We want S to be sparse because we don't believe that much of our image is corrupt. So we want S, our kind of corruption entries, to be a sparse matrix. And we want to minimize that rank plus L0 norm of S so that L plus S adds up to X, so that this is true. Now, this optimization problem here, it's always good to write down what you want to solve, but you can't solve this in any kind of a computationally efficient way because this is a highly non-convex optimization problem. Both the rank and the zero norm are not convex, and so you have no guarantee that you're going to find a solution to this before the universe grows cold. And so what the authors of this paper did was they introduced this convex relaxation. This is what we normally do, is that we introduce proxies for these norms. So these norms are non-convex and hard to work with. So you introduce proxies of those norms that are easier to work with. In this case, the proxy for rank is the nuclear norm, or the sum of singular values. And the proxy for sparsity is the one norm, or the kind of sum of the absolute values of the entries of X. So this is a convex optimization problem. You can solve this in a scalable way that works in a relatively computationally efficient manner. And what you get out will probably, with high probability, it will be promoting low rank L and sparse S. Okay, so this is how you actually solve the problem, is by running this minimization. There's all kinds of good details in the paper and in our chapter 3 about how you would actually compute this and how you can write your own code using kind of alternating direction methods or Lagrange multiplier methods to satisfy this. Okay, but that's what you actually do, is you're trying to find a solution to this ill-posed inverse problem where L is low rank. This contains all of the patterns in the data, and S is a sparse vector or matrix of all of the outliers in your data. Okay, and you do it this way. Good. So that's actually basically how it works. And in the original kind of paper, where you have this data set here, they actually applied it to this data set, and what they found was that they were able to kind of remove shadows from people's faces. So it's a little hard to see, but in some of these you have pretty large shadows. And what they were able to do is, from the limited information that was in the picture, the low rank part, they could subtract off the shadow and show you what the person's face would look like in full illumination. And then everything else, all of the shadows, would go in this kind of sparse matrix S. So that's a really cool demo of how this works. And you can also use it for things like surveillance, or if you have a license plate and you have lines going through it, so some of it's occluded, you can kind of back those out possibly. You could figure out what's under someone's mask. All kinds of interesting and maybe questionable technology that can come from this. Okay, but again, it's based on this idea that you are solving a regularized optimization problem, and that there is a convex relaxation so that you can do this on really big data problems. Okay. Good. And in the last part of this, I just want to point out that you can also apply this to fluid flows. So fluid flows and physical systems in general, engineering systems or systems from science, even though they are also very high dimensional, they often have low dimensional patterns. So in fluid physics, we call principal components analysis proper orthogonal decomposition, POD, same basic idea, where you can essentially decompose a very complicated system like this fluid flow into the sum of only a few kind of basis flows or eigenflows. So maybe you only need 10 principal components to describe this fluid flow. What Isabel Scherl has shown, so Isabel is a graduate student working with Brian Palagi and me, what she showed is that even if you have your fluid flow data that is massively corrupted with kind of salt and pepper salt and pepper corruption, that you can essentially use this robust principal components analysis, and you can decompose that into a low rank fluid, which is kind of the cleaned version of the fluid, and a sparse matrix of all of the outliers and corruption. And it's important to point out, actually, that regular principal components works quite well for white noise. So if you have a little bit of white noise everywhere on your data, regular principal components does a good job. Robust principal components is when you have this kind of big corruption and outliers. And it's a little hard to tell here because this is high res, but all of these little salt and pepper errors, this is not white noise added to my field. We basically made these values manually, like -10 or +10. So they're really, really bad outliers, and the original data has been obliterated in that salt and pepper, the salt and pepper corruption. And so you can do this, then you can actually compute the principal components or the POD modes. So the true modes, this is POD on the noisy data. This is robust principal components analysis. And what Isabel showed is that you actually get much, much better kind of decomposition of your flow when you run this robustifying technique. You can also use this to build models like these dynamic mode decomposition models, where we know for these periodic flows, all of the eigenvalues of the system should live on the unit circle in discrete time. But before doing this robust filtering step, you get terrible eigenvalues, kind of really, really bad eigenvalues. After RPCA, almost all of your eigenvalues are where they should be on the unit circle. So really great work by Isabel. You can read about it in this archive paper. She'll have a video on this soon, and I'll put a link up when that video is posted, kind of walking through this on many, many more examples. Last thing I want to point out, I actually talked about this in chapter 1 on the singular value decomposition when I talked about the Netflix prize and correlations in general. And so I thought I would revisit that example here in the context of robust principal components analysis. So we have the Netflix prize and matrix completion. And the basic idea here is that you have this massive imaginary, not imaginary like square root of -1. You have this massive matrix, think about it as a thought experiment, where for every movie in the database and for every single person in your subscriber list, you have this matrix of preferences. And here I've simplified it so it's just, +1 if you like the movie, -1 if you don't like the movie. But notice, and so people, have different preferences. And of course we believe that individual people there are principal components of movie preferences and of movies themselves. So maybe, the Terminator and Conan are more similar than the Terminator and the Fantastic Mr. Fox, right? These live in a principal component together, and so do different people. And so the idea here is that the vast majority of this Netflix matrix is empty. People haven't rated every single movie they've ever watched. They haven't watched all of the movies, or else Netflix wouldn't be in business, right? So the vast majority of these entries are unknown. And what Netflix and other recommender systems would love to do is infer, what would Alice probably think about Pulp Fiction? Or what would Bob probably think about the Fantastic Mr. Fox? So they want to fill in all of these missing values. And that's a very closely related problem to the RPCA problem. Okay, so for example, let's just do kind of a thought experiment here. Let's look at Dan and Ed, who they have a lot of overlap in their data. So they both like Pulp Fiction, they both like Fantastic Mr. Fox. One of them doesn't like Conan, the other one doesn't like Dazed and Confused. And so what you can kind of, this is just a guess, you can kind of infer that based on them having similar preferences some places, they might have similar preferences other places. Similarly, you can do this on a column like the Big Lebowski over here. For example, if someone like Bob, agrees on this movie, I'm already missing my, I'm already losing what I filled in. Yeah, so if Bob disagrees with Pulp Fiction, maybe he's going to disagree with the Big Lebowski, okay? And this is an example where I kind of did it by hand, so this is a little silly. But you can imagine that if this was a much larger matrix and it's much sparser, there are still all of these correlations. You can still cross-reference everything. It's almost like a really high-dimensional Sudoku puzzle, okay, where you are cross-referencing things and trying to figure out, based on someone liking this and someone liking this, what this other person would like, okay? But with these kind of robust statistics techniques and these regularized solutions for ill-posed inverse problems, and the fact that patterns exist in your data, there are ways of automating the solution of this problem. And so they're actually getting quite good at this in recommender systems. They're really getting good at inferring what the entries of a mostly sparse matrix would be, assuming that it has low dimensional patterns. Okay, so robust principal components analysis is super useful, really important. Again, you should definitely go check out the original paper, check out chapter 3 in our book, where we talk a lot about kind of sparsity in general and robustness and robust statistics. And download the code and try this yourselves. This is really powerful stuff. There's not magic happening here. It seems like magic because this inverse problem is ill-posed, but with the magic of regularization, with a judicious choice rather of regularization, you can do these pretty amazing things like robust signal decomposition. Okay, thank you.